If you want to, you can go to mathheals.com and find links to other YouTube videos under here. Let's take a look at the Poisson distribution. This is a discrete probability that applies to occurrences of some event over a specified interval. And this down here talks more about what those occurrences must be. Occurrences must be random, independent, and uniformly distributed over the interval being used. So you have a constant flow coming in, whatever that might mean. Now, x is the number of occurrences of an event over some interval. And our formula, probability of x, is equal to mu sub x times e to the negative mu power all over x factorial. Now our mu is mean, of course, but that's lambda times t, and we're going to talk more about that. And then sigma is equal to the standard deviation, of course, which is square root of u, or square root of mu, sorry. Let's take a look at this formula. Okay, got lambda is equal to 3, and that's a Greek letter. T is equal to 5, and it wants us to find a probability that x is equal to 12. Let's go back to our formula. For our formula, we need mu, so let's find that first.
A vast virus database has been updated.
Go away fast. Okay, mu is equal to lambda times t, which is 3 times 5. Excuse me, which gives us 15. Okay, so then probability of 12. We got mu to the power of x, so we got mu. Actually, we're going to write down the formula first. There we go. Times e to the negative mu power over x factorial. Okay, so we're finding x is equal to 12. Mu was 15, so we got 15 to the 12th power times e to the negative mu, so e to the negative 15, over x factorial, which would be 12 factorial. So the probability that x is going to equal 12, let's plug this in our calculator. So do a beginning parentheses, 15 to the 12th power, so 15 caret 12, times e do by second, ln. Then it puts the e, puts the caret, puts the beginning parentheses on there for you. Then negative 15. Closing parentheses on the e, closing parentheses on top of the fraction. Divided by 12 factorial. So 12, and then I'll do math. Left arrow over to PRB and choose number 4 for the factorial. And then enter. And we get 0.0829. Rounding to 4 decimal places. Now, one thing I'll mention about the formula, there is no tables on this, by the way, because your mean might be different on every problem. So you'd have to have an infinite number of tables in order to have it. So if you're going to do it by hand, this is how you have to do it. Problem with that is, if I had a problem where I got x is less than 70, for example, we'd have to do this formula for x equals 0, x equals 1, x equals 2, all the way up to x equals 69. So we'd have to do it 70 times to get our probability. So it's not good to do that by hand. we're going to look at technology. But first, let's talk about finding the mean and standard deviation. So we got another problem where lambda's given, it's 5, and t is equal to 10. And the instructions say find the mean and standard deviation. Our formula says that the mean, mu, is equal to lambda times t. So we'll take 5 times 10, which gives us 50. And our standard deviation is equal to square root of mu. Yep. Which gives us a square root of 50. Which gives us I'll take it 2 decimal places, 7.07. Okay. That was that one. Well, these were pretty straightforward. I mean, that formula wasn't necessarily that nice, but it wasn't that hideous. The part that throws people a little bit is finding lambda and t. And, well, we're going to see a few examples here in a second. But TI3, TI4 function, use Poisson PDF and Poisson CDF. Poisson PDF is when you got exactly one value, like x equals a number. And you see it says mean and then comma x. If I come up to this one up here, our mean was 15, so let's do Poisson PDF to find this. So I'll do second vars. You'll do an up arrow to get there faster, I think. We want Poisson PDF. And then we want our mean, which in the first problem number 1 was 15. This will tell me if I did it right by hand. And then comma, and then the x, which is 12. Enter. 0.0829. Okay, so that's how you do it on the calculator. There we go. Had trouble getting back here. Now, Poisson CDF is when you're adding up all the probabilities from 0 up to x. So, and we're going to see the different possibilities for that. So it's cumulative. It'll do this one right here. X is less than 70. It would do that for us. So without having to do the formula 70 times, without doing Poisson PDF 70 times, we can do it with one calculator function. Okay. Now let's talk more about lambda and t. When finding probabilities, step 1, identify the average number of occurrences of the event in some interval, lambda, and number of intervals, t. So let's look at some examples of that. Let's say that I can make 10 fat burgers per hour. Then, over 7 hours, ... This is kind of how the problems will be set up. Lead in like this many per hour, then looking at 7 hours. Blah, blah, blah. Find the probability of this or this. Okay, identify the average number of occurrences of the event in some interval. That's our lambda. Well, I can make 10 fat burgers per hour. So this is per hour. Then I come down here, then it says then over 7 hours. Well, t is the number of intervals. So t would be 7. So for this problem, our mean would be lambda times t, which would be 10 times 7, or 70. Let's say there's 8 potholes. This is on average per street. Then, looking at 5 streets, dot dot dot. Well, lambda. This is lambda is the number of occurrences, some event, and some interval. Well, we can have 8 potholes per street. So lambda is equal to 8. And that's per street. Then T will be the number of intervals. We're looking at 5 streets, so T is 5. So our mu here would be lambda times T, which is 8 times 5, or 40. Okay, now if they were all this simple, then it'd be fantastic. Wouldn't be too bad. Okay, so let's say the average is 2 per 10,000 miles. Then over the next 10,000 miles, dot dot dot. Okay, so the average is 2 per 10,000 miles. So lambda here would be 2. This is saying per 10,000 miles. That's our interval. For our T, then, we look to see, it says over the next 10,000 miles. So it's only one of those intervals. So T would be 1. So our mu would be lambda times T, which would be 2 times 1, or 2. Now, the last one's a little bit tricky because it doesn't fit our mu is equal to lambda times T format. But let me say there are, or there have been, 120 tornadoes over the last 50 years. And comma, over the next year, dot dot dot. Okay, now this is, you don't want to take 120 times 50. I'd have to actually calculate this. Tornadoes per year. Tornadoes per year means I'd do 120 over 50. And that actually would be our mu. Because it's asking over the next year. So we take 120, divide by 50. And that'll give you your mean. So that one's a little bit different. I mean, it really isn't, because if you come up here, your lambda is this is the number of, it's hard to put in this terms, but average number of occurrences event in some interval. To find an average per year, we take 120 divided by 50. So that's per year. And then time is asking over the next year, so telling you T is equal to 1. So it really does fit this. It just looks different because you have to do divide. And I don't know what that gives you, but that would be your mean. And let me save this page. Other than that, if you understood the binomial distribution, this one's a piece of cake. What did I just do? Try it again. Untitled. I guess that's one I just did. ES, Poisson Distribution. Page 01.pdf. There we go. Okay, so we want to identify lambda and T, and that's sometimes challenging. Calculate mu sub x, our mean, is equal to lambda times T. List the x values the problem entails and rewrite with inequality or equality symbols. And then use a table on the following slide to determine how to enter the function. Now we got 4 forms: x equals, x is less than or equal to, x is greater than or equal to, or x is between two numbers. We'll come back to this table. Let's look at some examples. So A. We've got probability exactly 8. actually, I guess I should write this stuff down. Poisson distribution with lambda t, or lambda is equal to 2, and t is equal to 5. Okay, so probably exactly 8. Our first step here is identify lambda and t. Well, that's already identified, so we don't need to find that. Find mu. Mu is lambda times t, so that'll be 2 times 5, or 10. Okay, now list the x values the problem entails. Well, this one is x equals 8, so that's just 8. And that's actually already in the equality symbols form. So then it says use table and final slide to determine how to enter the function. Well, the x equals a number is our first form. X equals a is just a number. So in this case, this is going to be our a. Now our form says Poisson PDF, and we do our mean, mu, and I'm not going to, well, I'll put the x there so it matches exactly. So mu sub x and a. Okay, so this will be Poisson PDF. Mu sub x is 10, and a is 8. So let's go put this one in. So I'll do a second vars, and I want Poisson PDF. So do enter on it, and 10 comma 8. And that gives us 0.1126 for our probability. Okay, let's look at B. Less than 17. Come back here. Step 3. List the x values the problem entails. Well, less than 17. That would be 0, 1. Less than 17 doesn't include 17, so it would go through 16. Write this second part of step 3. Rewrite with inequality equality symbols. So this would be the probability that x is greater than or equal to 16. Try it again. This is x is less than or equal to 16. There's a lot of noise going in the background here. Let's listen to that instead of this. X is less than or equal to a number. That's form 2. So this is going to be a. And we're going to use this. Poisson CDF, mu sub x, a. So Poisson CDF, mu sub x, and then a. So this is going to be Poisson CDF, mu sub x, what did we say that was, 10, and a is 16. So let's go put this in. Second vars, Poisson CDF, 10, comma, 16. Then we get 0.9730, rounded to 4 decimal places. Okay, let's look at part C. At most 12. Well, back to step 3. List the x values this entails. At most means 0, 1, all the way up to 12. So it includes 12. Second part of step 3, rewrite with inequality equality symbols. Well, this is x is less than or equal to 12. This is like the one we just did. So this is going to be our a. And we're going to have Poisson CDF, mu sub x, comma a. So this is Poisson CDF, mu sub x, that's still 10, and A in this case would be 12. So let's put that in. Second vars, Poisson CDF, 10, comma, 12. And then enter. And I'll take it to four decimal places, so 0.7916. And that'd be our answer. Okay, so D. Probability more than 20. Well, the Poisson distribution, it's uniform, comes in an even flow, but there's no limit. You know, for example, Walmart, or no, actually McDonald's. Pick on McDonald's. They may have an even flow of customers coming in. Well, how many can they get? Well, could they get 100 people coming in lunchtime? Yeah. 200? Yeah. 10,000? Could everybody in, for example, Arc City, I think that's about 12,000 actually, could everybody in Arc City go to McDonald's at the same time? Yeah, that'd be about 12,000. And I'm saying same time, I'm talking about between 12 and 1. So it's an even flow of 12,000 people in that time frame. Yeah. Could everybody in Wichita go down to Arc City and eat at McDonald's? Yeah, it's a possibility. Not very likely. Very, very small probability. But we could have let's say 350,000 people come into McDonald's in Arc City. Could everybody in the world go into McDonald's between 12 and 1? That's a possibility. They could build rafts and come over, or maybe they got the best McDonald's ever. So we treat it as infinity. We know there's actually a finite number of people on Earth, but we treat it as an infinite amount. So when I say more than 20, that would be 21, 22, forever. So now, second part of step 3 says to rewrite with inequality symbols. This is saying that x is greater than or equal to 21. So let's use our table now. X is greater than or equal to a number is our third form. So this would be A. And the formula it tells us to use is 1 minus Poisson CDF. And it says mu sub x, comma, A minus 1. So we'll have 1 minus Poisson CDF, our mean, which is still 10, and A, which is 21 minus 1. So we've got 1 minus Poisson CDF, 10, comma, 21 minus 1 is 20. So to put that into our calculator, we'll do 1 minus second vars, choose Poisson CDF, 10, comma, 20. Wife's killing me with these chemicals. She's cleaning the bathroom. Closed my window because I got cold, but I'm going to have to open it back up, I think, so I can breathe. 0.0016. Mind you, I'm not complaining. I don't have to clean it. And it probably needed cleaning, though she does a fantastic job and didn't look clean. Didn't look like it needed it to me. Okay, E. Probability at least 25. So at least 25. Step 3. List the x values the problem entails. At least 25 includes 25. So we're going to have 25, 26, up to infinity. Okay. Second part of step 3. Write this with inequality symbols. This would be x is greater than or equal to 25. And now it's similar to the one we just did. It's greater than or equal to. So this is going to be our A. And our formula, if we look it up on the table, is 1 minus Poisson CDF mu sub x A minus 1. So we got 1 minus Poisson CDF mu sub x that's still 10. A So 25 minus 1, which is 1 minus Poisson CDF. 10, comma, 25 minus 1 is 24. So we got 1 minus second vars, Poisson CDF, 10, comma, 24. Enter. So we get 4.694 E negative 5. Okay, this is scientific notation. This means 4.694 times 10 to the negative 5 power, which means I moved my decimal place 5 places to the left. So it'll be 1, 2, 3, 4, and then 4, 6, 9, 4. And that'd be our answer. Well, let's look at our last one. Oops. F. So, probability between 10 and 20 inclusive. So it includes those values. Okay, step 3. List the x values. Between 10 and 20. That'd be 10, 11, all the way up to 20. So it includes those values. Second part of step 3 is rewrite with inequality symbols. Well, this is the between case. So 10 is less than or equal to x is less than or equal to 20. Use our table now. This matches our fourth form. So this is going to be 10 is going to be the A and 20 will be the B. And our formula, or form I guess I should say, Poisson CDF mu sub x B. So mu sub x B minus Poisson CDF mu sub x A minus 1, I believe. Yeah, A minus 1. Okay, so this becomes Poisson CDF mu, which is still 10, comma B, which is 20, minus Poisson CDF mu, which is still 10, and then A minus 1, which would be 10 minus 1. So that gives us Poisson CDF 10, comma 20 minus Poisson CDF 10, comma, and 10 minus 1 is 9. So let's go put this in. So second vars, up arrow, and choose Poisson CDF 10, comma 20. Close parentheses minus second vars, and I want to up arrow and choose Poisson CDF 10, comma 9, and then close parentheses. And our answer then will be 0.5405, rounding to 4 decimal places. 5405, yeah. So let me save this. There we go. I think that's last. Yep, that's the last one. So let me stop the recorder. And this is the Poisson distribution.